we are now going to be live on YouTube. Not live. I could do that, but no. So limits. What is our first unit is on limits. What is the idea of a limit? It's kind of a value that you can get really, really close to. And you've had some introduction to limits in the past. When you took infinite geometric sequences way back in grade 11, and you added up numbers like 8 plus 4 plus 2 plus 1 plus a half, and you kept on going, you had a formula. Do you remember this sum to infinity formula, which was T1 over 1 minus R? R was the common ratio. We're multiplying by a half. Term 1 is 8. You could plug those numbers in, and the formula would tell you it should equal 16. Well, this is the concept of a limit. Because if I start 16 tiles away from the wall, and I always walk half the distance to the wall, in my first step, I don't know if I can do it in one step, but in the first time, if I'm walking half the distance, I'm going to walk 8 blocks. And then if I walk half the distance, I'm going to walk 4 blocks. Now I can step. Then 2 blocks, then a block, then a half a block, then a quarter, then an eighth, then a 16th, then a 32nd, then a 64th. Whew. And on and on and on. Will I ever get to the wall? No. Theoretically, I will never get to the wall because I always have a little distance left and I only go half. But if I did that forever, how far have I walked? We could say that you could get as close as you wanted to the wall. If someone said, no, you can't get closer than this to the wall, you say, well, when I get there, I'm going to go half the distance. I'm going to get closer. So we can get arbitrarily close to the wall, and I would say the limit, as I would do this forever, would mean that I would walk 16 spaces. It's a value that I get close to. I never actually walk 16, but I can get so close to 16 that we would say that in the end, the sum to infinity of this is 16. Now, for the calculus that we're going to learn this semester, there's sort of 2 main branches, integral calculus and differential calculus. Even though integral calculus was worked on way before differential calculus was, differential calculus was co-invented, not co-invented, but invented simultaneously by both Leibniz and Newton, you can trace back integral calculus all the way back to the Greeks. Archimedes is sometimes called the father of integral calculus. He called it a method of exhaustion, of when you do something over and over and over again until you can say that you're basically so close to the right answer that you have the right answer. And then, as I said before, differential calculus, much later, 17th century. Now, historically, if you were taking calculus and you were in an English-speaking world, all the calculus books originally in English-speaking world would have said Newton discovered calculus, because Newton was English. And if you had any German textbook and you were learning calculus in Germany, it would say Leibniz discovered calculus. Because they didn't have the internet back then. It's not like someone posted it first and then somebody else read it and then they did something afterwards. They were sort of working on their own. And even though there was a number of years between the two, it's now considered historically that they both discovered the same thing on their own, but in different places and in slightly different times. Now, with the way that our world is, you can't really, someone discovers something, puts it on the internet, and everybody has access to it, and then 5 years later you go, oh, I figured this out on my own. You're like, well, I don't know. But back then, that was okay. So we get to do, before we get into our limits, we have to warm up some of our algebra skills from the past. So some of those skills that, factoring. Oh, shouldn't have the answer there already. Factoring, remembering how to factor that you first did in grade 10 is super, super important and comes back again. This is one of my favorite simple factoring ones. So a couple things about factoring. Okay. Ooh, how many people are coming from French immersion? 1, 2, 3. Okay. We get to introduce you to some English math lingo. Okay. Now, when you factor something, these ones here, the x squared, that x squared comes from the first terms. When you multiply the first term in the binomial, which is x, times the first term in the binomial, and the other one, x, you get x squared. Okay? The last ones will always multiply to get that number. So now we have some options, right? It could be 1 and 24, 2 and 12, 4 and 6. And when you multiply it out, the outside and the inside combine. I'm going to change the color of that. I'm going to show you. I'm going to put down the answer. The answer to this one happens to be plus 12 and minus 2. Okay? The outside and the inside combine to get that plus 10. And I like this one because most people try 4 and 6 first. Because that also makes 24, and 4 and 6 also makes 10. But it doesn't work. And in English, when you have a binomial times a binomial, sometimes they say, oh, what you need to do is FOIL. You have to multiply the first ones, then the outside ones, then the inside ones, and finally the last ones as a way to remember it. Have you ever heard your English math counterparts say FOIL and wonder what they meant? Or did you learn, or do you use FOIL in French as well? No, there's no foiling around in French. Okay. So that's where FOIL in English comes from. It's just an acronym to remember how to multiply. And when we factor, and there's different methods for factoring, but one of the things that's good to do when you're finished factoring is to multiply it out to check to see if it works. So our first couple factoring ones, well, this one is straightforward. It's one you've done before. Oops, I want to erase that so you don't see the answer before I put it up. There we go. If you can factor this one directly, that's great. If you have techniques that you've developed in the past for factoring that you'd like to use, those are great as well. One of the things that this one gets you to remember for factoring is a common factor. Notice how in all three terms there's an h. So we can start by noticing that and factor that h out first. And then the question is, can the rest be factored? Can we factor what's left even more? Whew, so much good math coming up. So what's usually one of the things that happens when you try to factor something that may or may not be able to factor. You try a bunch of things, and if none of them work, you start to feel like it can't be factored. Can that one be factored? Don't know. I mean, if it could, my first ones would have to give me 3h squared, and my last ones would have to give me 1. If it could be factored. If it could be factored, and the first ones have to give me 3h squared, there really is only one possibility for my first ones. Can you see the only possibility would be 3h and h? You can't get 3h squared any other way because 3 is a prime number. And with 1, the only way to multiply to get 1 would be 1 and 1. With that in mind, do the outside and the inside make 7? No. This is done. Can't factor it any further. Mathematically, if you wanted something formulaic, something like, how could I know for sure if something factors nice? You could use your quadratic formula. Oh, okay. This is, I don't know if there's ever really a good time for this, but on this course, there is no formula sheet. So all the formulas from the past that you would like, you have to know them. Oh, I'm sorry. So quadratic formula. Do you remember your quadratic formula? No. Well, this is the first one you can practice memorizing. There's your quadratic formula. Part of your quadratic formula is this part. It has a name. It's called the discriminant. And any time the discriminant works out to be a perfect square, like 4, 9, 16, 25, whenever it's a perfect square, you can square root that number easily, and you have all integers. And anytime you have all integers, that means it could factor nicely with nice numbers. Anytime the discriminant is not a perfect square, like the square root of 10 or the square root of 15, something you can't take the square root nicely, that's when your term cannot be factored nicely. So in this case, if I would look at the discriminant, which is 49 minus 4 times a times c, 49 plus 12, 61. 61 isn't a perfect square, so I can tell right now that I would not be able to factor that algebraically using that part of the formula as well. Okay. Whew, we got into that's some complicated review with just factoring already. And don't worry, this is review, but we will learn some real new stuff already today, because I couldn't just have a math class without learning something new. Some other factoring that we've done already. 9x squared minus 25. In English, we call this a difference of squares. Why do we call it a difference of squares? Well, the word difference comes from the fact that we're subtracting. And both of these are perfect squares. 25 is 5 times 5. 9x squared is 3x times 3x. And so when factoring a difference of squares, the first one's, that's 3x and 3x. The last one's 5 and 5. One is positive, one is negative, because your outside and your inside cancel out. Technically, a difference of squares is really 9x squared plus 0x minus 25, and you could use the same rules or shortcuts or whatever methods for factoring trinomials that you had in the past with just a 0 there. But in math, we don't write 0 because it would be kind of redundant. And there's a whole bunch of other 0 things we could write that aren't there. And you could write forever with a bunch of zeros. But it doesn't really help us. So we instead give something a name. We call it a difference of squares. And if we can remember the name, then it helps us remember a strategy for factoring that. And it becomes 3x plus 5, 3x minus 5. So again, all the factoring that we've had so far, factoring out a common factor, factoring a trinomial, factoring a difference of squares, this has all been review. So now let's look at something a little bit different. Let's factor with some negative exponents. This you have not done before. So you've got 1 plus 5x to the negative 1 plus 6x to the negative 2. And you want to factor it. Okay? Why do we factor things? Well, we factor things because sometimes you have an equation like this equal to 0, and you want to find out what value would make that equal to 0. So with the negative exponent, we're going to factor out that smallest exponent, in this case an x to the negative 2. If I take out an x to the negative 2 as a factor, and you think about distributing, what would be here to give me 1? What would have to be there? X squared. Does that make sense? If I put an x squared there, that an x to the negative 2 times x squared would give me 1. And here, x to the negative 2 times what, use your exponent laws, would give me 5x to the negative 1. Well, it would have to be a 5, right? And I would have to have an x to the 1, so when my x to the negative 2 is there, we add our exponents and we get x to the negative 1. And if I took the x to the negative 2 out of the 6, I'd just be left with 6. And what did we do by taking out the x to the negative 2? We changed our inside to something that we recognize and know how to factor. That's kind of neat. So what does this mean? It means if this was equal to 0, this would be equal to 0, and this would be equal to 0. And that would tell us that these two things would be answers to that equation. Plug in negative 2 and check it. Does it equal to 0? Anyways, that is where we will stop for today.